My talk will be about artificial neurons. I'm certain all of you have already heard of the term artificial neuron or artificial neural net. And what I'm trying to do in this talk is finding out what we mean when we use this term and to see if we refer to something like real neurons or something similar, maybe as in artificial hearts, for example, or whether we are speaking merely metaphorically. The question I'll try to answer therefore is the following: how neuron-like are artificial neurons? More precisely, can artificial neurons perform the biological function of neurons? That is, can there be functional analogs of real neurons? The talk is structured as follows. I will start out in the first part by introducing 3 different kinds of systems that have been labeled artificial neurons to see how diverse the use of this term actually is, how different the different systems are that have been termed artificial neurons. And in the second part of my talk, I will focus on biological functions, the biological functions of neurons, and see whether artificial neurons can fulfill them. So then let's start out with the first example of an artificial neuron, which probably is the most famous one. Like the use of artificial neuron as we use it in deep neural nets, for example, or artificial neural nets in general. ANNs, or artificial neural networks, first and foremost are mathematical abstract objects, therefore are not really in some sense similar to biological neurons, but most of the artificial neural networks are implemented in some physical hardware or another. So what we might mean when we speak about artificial neurons, therefore, is the implementation of such an artificial neuron in, let's start out with, standard digital hardware. Neurons in a neural net are basically nodes that stand for a number. This number is stored usually in the random access memory of a computer or of a server. So the first use of artificial neuron would be precisely that. Here on the left-hand side, you can see a standard digital RAM. And this RAM, random access memory, uses transistors, either charged or discharged transistors, to store that number, which represents the neuron in the artificial neural net. Usually it's not one transistor that stores the number, but a whole range of those transistors. And this range of transistors that stores the number of our neuron, that's the first use of artificial neuron that we're going to consider. The second way we might use the term artificial neuron, actually the second and the third, both are connected to so-called neuromorphic hardware. What neuromorphic hardware tries to do is not only simulate the brain in some sense, but to replicate, to duplicate some of its structure in hardware. And we will be looking at 2 different artificial neurons in the context of neuromorphic hardware. The first artificial neuron in this concept might be neuromorphic cores. What do I mean with that? Like very big scale, or some very big scale neuromorphic chips work in such a way that they interconnect large numbers of processors or of processing cores. For example, here on the on the right-hand side, we can see a Spinnaker board. Spinnaker is a huge neuromorphic computer currently under development, I think, in Dresden, either in Manchester or in Dresden. It's a collaboration of both universities. And what they are doing is they take those processing cores and really wire them together. And not only some, but quite big numbers. Here, one board has 864 of those cores. I don't know how many boards they use in the entire architecture, but I think it's, at least in the latest version, up to 1 million cores in total. And those cores are also referred to as artificial neurons. One might say that Spinnaker 2 consists of a million artificial neurons. What we mean by that is that it is made up from 1 million of those processing cores. That's number 2. Let's move on to the third use of artificial neuron, which again is in the context of neuromorphic hardware, and especially in the early days of neuromorphic computing. The idea then was to really build physical systems with the same dynamics as biological neurons. So what we can see here on the right-hand side, that's a comparison between the spiking behavior of a biological neuron, of a real neuron, upon receiving a stepwise input current. And the same current has been fed into this silicon device. It's a silicon neuron in that case. And you can see that the spiking behavior, like the electrical dynamics, the spiking dynamics are almost identical in the silicon and in the biological substrate. So that's the third sense in which we might use the term artificial neurons. Okay, now before I turn to the biological functions of neurons, 2 assumptions. First of all, I need to assume that the capacities of the brain, that is, all capacities of the brain, including phenomenal consciousness, can be explained mechanistically. If not, the entire idea of having biological functions spelled out in the way I will present doesn't make much sense. The second assumption is that the right level of description is either at the neuronal level or above, since I will be talking about artificial neurons and not, for example, about artificial dendrites or whatever lower level elements you might have. Okay, here is basically my definition of what a biological function is, or what a function is in general. I take this from Craver 2001. In his sense, the function of an item or a trait is the causal role it plays within a mechanism. What does that mean? First of all, let's maybe start out with 2 more or less standard examples of mechanisms. On the left-hand side, we can see the so-called Watt governor. And on the right-hand side, we can see the cardiovascular system of a human. And now if we were to ask, what is the function, for example, here on the left of the flywheels of the Watt governor, we need to see what is the causal role the flywheel plays within the Watt governor mechanism. And what is that causal role? Well, if the flywheel starts spinning, it's supposed to lift that lever up here, which then again closes the valve, which reduces the gas flow. So the causal role the flywheel plays here is lifting a lever when the the rotation frequency has a certain number. In the case of the cardiovascular system, we again might, for example, ask the question, what is the function of the heart? In the very same sense as in the case of the watt governor, we would say the function of the heart is the causal role it plays within the mechanism of the cardiovascular system. The mechanism here would be like the heart pumps blood, the veins carry it to the body, the liver purifies the blood and then pumps it back to the heart, something like that. And the causal role of the heart in this case, the causal role it plays within that mechanism is pumping blood. That's like what the heart does. So from the perspective of Craver, we would say the causal role function or the biological function of the heart is pumping blood. What will be interesting when we talk about computers and when we talk about the brain are also computational mechanisms. Let me give you a brief definition of what a computational mechanism is. A mechanism is called computational if and only if it can be stated without reference to physical states and causal laws, that is, if and only if it is medium independent. So a mechanism is computational if it can be stated in a medium independent manner. Well, what do I mean by that? A standard example is the Turing machine. Like if we look at the Turing machine, it can be stated completely by basically only giving the state table. And when we look at the state table, what it tells us, okay, we are in state Q0, then read a 0, we write something, then we move, and we change the state to Q1. So what the state table tells us is, okay, change your state from Q0 to Q1 in the first case. It does not say anything about the nature of those states. Those states might be charged and discharged capacitors, they might be levers which are either up or down, switches which are on or off, they might be whatever you want, whatever you can think of. Everything that matters in this case is that the system under consideration can be in enough states and changes its states according to the program. What kind of states these are, like the specific nature, that's irrelevant. That's what I mean by medium independent. And we would say that a mechanism is medium independent if it can be specified completely without any reference to the special physical states. Okay, now the question is the brain a computational mechanism? Is what happens in the brain, can that be stated medium independently? If that is the case, then the function of the brain, the function of a neuron is changing its state in accordance with a program. And in accordance with the program means such that the mechanism implements the program. So all we need is a mechanism that implements the program with which the brain computes. Now the question is, which artificial neurons then could be functional analogs of biological neurons if the brain is a computational mechanism? And the answer is quite simple, all three kinds of artificial neurons. Like if we had the right kind of program, that is the program that's carried out in my brain or in our brains, then we can implement it in any kind of hardware. And since computation is medium independent, it doesn't matter which kind of hardware it is it neuromorphic or is it digital, doesn't matter. So all three kinds of artificial neurons might be used to implement the computational function of a neuron. So yeah, but what is if the brain is a non-computational mechanism? Much like the what governor, for example. If the brain is a non-computational mechanism, then the function of a neuron is to produce output spikes in response to input spikes, electrical signaling. That's the causal role a neuron plays within the biological mechanism of the brain, if the brain is indeed non-computational. Spiking or electrical signaling in that case is the causal role that neurons play. And now if that is true, like if the brain is really a non-computational mechanism in that sense, then only spiking neurons, like neurons from the third category that I showed you, can be functional analogs in the right setting. Also, what I maybe should briefly mention is this "in the right setting" clause. What I mean by that, I do not want to claim that an artificial neuron in isolation might in some sense be a functional analog to a neuron in my brain. The function of the neurons in my brain, that depends on the context, like on the other neurons with which it is wired together. So what I mean here with "in the right settings" is that, like, if I were to place such an artificial neuron in the appropriate mechanism, it would be able to fulfill its function. That's what I mean by "in the right setting," if it were built into the right kind of mechanism. Okay, so we talked about two options. Either the brain is a computational mechanism or it is a non-computational mechanism. Seems as if we had exhausted all the possibilities. However, we have not. There are some hybrid versions, like for example the integrated information theory, which does not consider the brain to be a completely computational mechanism, also not to be a completely non-computational mechanism. But the idea of IIT, for example, is that, well, there are entities that kind of have and process information in a computational manner, like in a medium-independent way. But however, the connection between those entities, that's not medium-independent. We need real physical causal connections between those computational elements, in the case of IIT. And if IIT is correct, then the function of a neuron is to physically integrate information processing entities. Like I already said, in that sense, IIT is a hybrid between computational and non-computational elements. And integrating information in that case would be the causal role of neurons. And now let's see whether artificial neurons can play that role. And we see that, okay, digital hardware is not capable of implementing or of playing the biological role if IIT is right. That is simply because the integration density, the fan in and fan out of standard digital computers is way too small. Therefore, they cannot integrate enough information. However, neuromorphic computers can, and therefore neuromorphic cores and spiking neurons can be considered functional analogs if they were put in the right settings. Okay, so that's the picture that we get in the end. If, let's say, computationalism is true, then consciousness is medium independent. Everything relevant that happens in the brain is medium independent. And it does not matter whether we implement it either in the brain, in standard hardware, in neuromorphic cores, or in spiking hardware. Therefore, all three kinds of artificial neurons might be functional analogs of biological neurons in the right setting. If the brain is an essentially non-computational mechanism, then what matters is electrical signaling or spiking, and only spiking neurons in neuromorphic spiking hardware can be functional analogs of biological neurons, again, in the right setting. If hybrid accounts, like for example IIT, are correct, and it is more about integrating information rather than processing it, and also rather than spiking in the end, then neuromorphic cores and spiking neurons are capable of serving the right kind of function. Standard digital hardware cannot, like artificial neurons implemented in standard digital hardware cannot be functional analogs of biological neurons if IIT is correct. So if there is any slide that you might want to screenshot, it is this. That's basically the result of the entire talk. Okay. Those were my references, and if I may, I'd like to end with a brief advertisement together with Gattiero Piccinini. I am co-editing a special issue on the philosophy of neuromorphic computing or of neuromorphic hardware at the newly founded Journal of Philosophy of AI. And we'd like to invite everyone who is interested in neuromorphic computing, in neuromorphic hardware and the philosophy thereof to contribute to our special issue. And now I'd say that's it from my side. Thank you very much for your attention. And if you have any comments or any feedback, feel free to contact me either via email or X or Blue Sky, as you wish. Thank you very much.